This is a rough go, guys. You know, but we gotta stick to it. We're almost done. This section will be done, and this actually is the last slide that actually has new material with it. Okay, so here we go. It says here, find the area of the region between the curve y equals 4 minus x squared from 0 to 3 and the x-axis. All right. So as you can see, the shaded area here, I've got two sets of shaded area, right? I want to find this, and I want to find this. But what makes the fundamental theorem of calculus great is I don't have to set this up as two separate integrals and add it together. The fundamental theorem of calculus told me that if I take the integral from 0 to 3, 4 minus x squared dx, I need to come up with a function big F that when I take the derivative I get 4 minus an x squared. So that's what you just got to be thinking about. What would be big F? So 4. I look at 4, I say, well, what function when I take the derivative gets me 4? Well, that's just going to be 4x minus, I got to think what function when I take the derivative gives me a negative x squared. Well, I know it's got to be something with an x cubed, and I'm going to divide it by this new number on top, 3. So that's my big F. 4x minus an x cubed over 3 is big F. And it said that if I evaluate it from 0 to 3, that is, if I find what big F of 3 minus big F of 0, that's what this is saying up here. So what does that equal? Well, I plug 3 in. And when I plug 3 in, I get 12 minus 27 over 3. And then I subtract f of 0. I subtract f of 0, well, that's 0. Plug 0 in both of those. Alright, well, 12 minus 27 over 3 is 12 minus 9. It's equal to 3. This is where your brain has just got to explode just a little bit, guys. That the positive area up here minus this area down here gets me 3. Exactly 3. 3 square units. How amazing is that? Right? Amazing. Alright? So what we're going to do over the next several here, because that's all the slides for this setup, and homework part 3 is here, 41 to 48 odd, okay, all in your book. Okay, these next set of slides here are going to be all about what types of problems you can else see in your book, and hopefully a little bit of a review and a little bit of help for you on these problems. So on these here, they're asking you for number 6. This was straight up as being, hey, take the derivative of the integral. Hey, look, is it a number? Yes. Is it x all by itself? Yes. So that means the derivative of my integral, I just replace the u with the x. ln pi x. Boom. That's it. I'm done. But when I come over here, again, this is a little bit more difficult because they're saying find the derivative of this. Well, is it a number? Yes. Is the top one just x all by itself? No. So this is where I have to come up with another variable. I'm going to call it u is equal to x squared. And then I go ahead and replace it in there. So that means that now I have not f of x, but f of u is equal to the integral from 2 to u sine t cubed dt. And then when I take the derivative, well, what does that mean now when I take the derivative? That means I'm taking the derivative of u with respect, the derivative of f with respect to u. Okay. Well, when I do that, I go through the same process. Well, that's just going to be sine of u cubed. Oh, okay. But I don't want df du. What did I want? I wanted this, which is the same thing as saying df dx. Derivative of f with respect to x. Oh, and remember, that's where I have to come into here and take the derivative of this. So when I take the derivative of u equals x squared, I get du dx is equal to 2x. And then I'm going to say, well, then I can multiply df over du times du over dx, and I'll get df with respect to x. And that's going to equal sine u cubed times 2x. And then when I rewrite this, the 2x can come over here, and the sine of u, well, it's not u anymore, it's x squared to the third power, which again I can simplify to be 2x sine of x to the sixth power. You need to go through these steps, okay? You need to understand them. All right? Next. Okay. Number 7 says here, if f is a continuous function such that f prime of x is equal to f of x, capital F prime of x is equal to f of x, then the integral from a to 7 of f of t dt, well, again, you got to ask yourself, what is this saying right here? Okay, what is this saying right here? This is saying what function, when I take the derivative, gets me f of t? They kind of give me that. What function? They say, well, f prime gets you f. So that means this right here, by the fundamental theorem of calculus, is, well, once I find that function, it's just going to be simply f of 7, capital F of 7, minus capital F of a. Answer choice on this one would then be D. So here's what I want you to do. I want you to use that same type of logic that I did up there for number 7. I want you to try out number 9. Okay? Same logic, and then I'll pause the video, see what you get. Think about it. Truly think about it. Here we go. Bang. There's the answer. Did you get it? I want to show you something, because you're going to use the fundamental theorem of calculus. Says that the integral from 1 to 4 of a f of x dx is equal to capital F of 4 minus big F of 1. Well, then I can just substitute in. They tell me that this integral is equal to 3.6. I'm trying to find out what big F of 4 is. They tell me big F of 1 is 2. And solve for big F of 4. Okay? Let's see what's next. Alright, this one we're going to have to spend a little bit of time with. Alright? So, there we go. If f is a continuous function from 0 to 9, and g of x, capital G of x, is equal to the integral of 0 to x f of t dt. Find g of 0. So I'm going to plug in for 0. See? G of 0 is equal to the integral from 0 to 0 f of t dt. Well, what's an integral from a number to the same number? 0. Part B is a little bit more interesting. They say, on what interval is g increasing? Okay, so again, what is g measuring? As x gets bigger, okay, so when x is 1, here is this area up here is what g is equal to. When x is 2, this area represents it. Did I get more area? Yes. So how much longer do I keep going until I get my area stops increasing? Until the integral part stops increasing. I get more and more area up to here. It's all above the x-axis. So at that point, then when I switch over to where it's below the x-axis is when I start decreasing. So g is increasing on the interval from 0 to 5. And vice versa, I am decreasing when my area is below the curve, or below the x-axis. And therefore, this is when I'm going from 5 to 9. Part D says, where does g have a maximum value? So I'm going to start trying to figure out here Where do I want the maximum value to be, or how does the maximum value work? If I were to do a little graph here of g of x, okay, and this is x. Well, up to 5 we said we were increasing, and after that we said we were decreasing. Okay, but which one's bigger? Did I increase more than I decreased, or did I decrease more than I increased? Okay, well, as I'm going through this, I feel like I increased more. So I kept increasing. My increases got smaller and smaller, so here I'm doing this. Then I start decreasing. And then right here, okay, my decreases start getting smaller. Okay, and here is 9. There is 5. So, and I knew that this point was 0, 0 because of my find A. Okay, part A. So where do I have a maximum value? Okay, when x is equal to 5. That's where it has it. So now I gotta ask myself, is g of 9 positive, negative, or 0? So again, why did I not go all the way down? Why didn't I take this curve all the way below the x-axis? Well, and looking at the areas here, I was like, well, the area above the x-axis is greater than the area below the x-axis. So I'm not going to go down as much as I went up. So that is why g of 9 is positive. Next is, for part F, is where does g have a minimum value? Well, because I'm positive at g of 9, okay, then my minimum value happened at g of 0 when x is 0. That's where it happened. The value itself is 0 as well. Now part G, that's an interesting problem. So, on which interval is g concave up? So I'm going to do this two ways. I can take a look at the g graph that I sketched myself, and I can say that someplace between here, I can call it halfway, between 5 and there, I can say 7, and 9, it starts being concave up. But how can I show that given the graph that I was given in terms of f? Well, I can say that on the interval that g is concave up. Well, let's look. What does it mean to be concave up? That means that g double prime of x has got to be greater than 0. Okay. But what is g double prime? Okay. We're taking a look at how they defined this up here. To me, it looks like g prime of x, if I take the derivative, right? Is the bottom a number? Yes. Is the top just an x all by itself? Yes. So what does that make g prime? F of x. Well, then what's g double prime? If I take the g double prime of x is then equal to f prime of x. If I want g double prime to be greater than 0, that means I want f prime to be greater than 0. What does it mean for f prime to be greater than 0? Okay. That means that f is increasing. Since I want that, that means that f prime of x has to be greater than 0, which means that f of x is increasing. Where does that f of x increasing happen? That happens between 7 and 9. That's a great question, and you should expect to see something like that. Okay? It's one of those thought-provoking questions. All right? All right, let's see what's next. Last one. It says write a tangent line equation for that. Woo! Tangent line equation. First thing through your mind, it's got to be going, I need a point, I need a slope. Hey, they give me a point, they give me a piece of it, x is going to be pi. Well, then I got to go find f of x, or f of pi. is equal to the integral of pi to pi cosine to the fifth t dt. This could be a problem up to the point where I go, wait a second, integral from same number to the same number. That's just going to be equal to 0. Well, I need a slope. So what does that mean? I need f prime of x. Well, what is f prime of x? So I'm going to take the derivative of this integral thing. So what does that mean? That means that it's going to be, well, I'll take a look. Is it all by is the number all by itself? Yes. Is this an x, just plain old x or plain old variable? Yes. That means f prime of x is just cosine the fifth of x. Great. So now what can I do? Now I want to find out, oh, f prime of pi equals cosine of 5 pi. Okay, well, cosine of pi is equal to negative 1 to the fifth power, which is equal to negative 1. So my slope is negative 1. There's my point. So it'll be y minus y1 is equal to negative 1 pi x minus pi. And simplify everything. Y is equal to a negative x plus a pi. Find out which one that is. Oop, there it is, D. D seemed to be a good answer this time through. Okay, this is actually an important one as well. It says a particle starts at x of 0 is equal to 2. If its velocity is given by that velocity, natural log of 1 plus t, find its position at t equals 5. So this is where you have to start remembering that it's asking for the position at a time is equal to 5. So in order to find the actual position, okay, I'm asked to find my final position. Alright, so in your physics background that you have, you should say that final position is equal to your start position plus, okay, displacement. Okay, so final position in this case, they're saying that means I want to find out what x of 5 is. Well, x of 5 is equal to my start position, x of 2, plus the integral from 0 to 5 of my velocity. Wait, that looks a little familiar. How did that happen? How does this happen? Well, this is what's amazing. This is amazing because that should be like, wait, didn't I have by my fundamental theorem of calculus? No, I'm going to go on a little tangent here. My fundamental theorem of calculus said that the integral of 0 to 5 of velocity dt, well, what is that equal to? So again, that's equal to what function when I take the derivative gets me velocity? Position. Okay? And that's going to be x of 5 minus x of 2. And if I solve for x of 5, my position function, look what happens. Integral from 0 to 5 v of t dt is equal to, equal to plus x of 2 is equal to x of 5. So this whole final position equals start position plus displacement is all a big use of the fundamental theorem of calculus, which is amazing. Think about this. Newton was amazing when he came up with this. Truly amazing. So now I go over here and I just solve. Well, okay, well, x of 2 I know. Well, that's 2. How can I find out this big business here? That's where a calculator comes into play. I've already taken the liberty to go ahead and put that in y1. So I'm going to go ahead and hit second, quit. And I'm going to again go Math 9. And I'm going from 0 to 5 of vars, y vars function y1 dx. And I hit enter. 5.751. 5.751. 2 plus 5.751, which is equal to x of 5, which is equal to 7.751. Answer choice B. Amazing stuff. This is just truly amazing. All right. Well, now you gotta have fun with your amazing. Here's this homework, book section 5.4. Enjoy. Look forward to talking with you guys later.